All right, we are going to continue talking about gases. And so remember last class period, the last thing I did at the end of class was the little demonstration of taking a bulb of fixed volume, right? It was made out of metal. It wasn't going to expand or contract very much. It does a small amount. When I changed temperature, and when I put it in hot water, what happened to the pressure? It went up. So that's one of the first, pressed the wrong button. One of the first things we learn about gases. And it's actually, I need to define an ideal gas because we're going to talk about ideal gases here. We're not going to talk about real gases. Real gases are better explained using an equation that we call, well, if you were Dutch, you'd probably say Van der Waals equation. In America, we just say Van der Waals. Van der Waals equation takes into account the fact that gases are not ideal. But before we talk about an ideal gas, we need to know what an ideal gas is. So ideal gases have just two properties that distinguish them. First, the atoms and molecules don't interact unless they collide. So what that's saying is, they can't have an electric charge because they have an electric charge and they pass by each other. They're going to interact. So plasmas would clearly not be ideal. And when they collide, they need to have perfectly elastic collisions. They need to not stick together at all. So they need to act like billiard balls, essentially. So that's our first rule. They need to be non-interacting except for when they collide, and then they just have elastic collisions. The second one is the atoms and molecules have to have zero volume. Very, very realistic, right? Okay, so neither of these are perfect approximations ever, but they're really good approximations in the right situations. If you have something that's moving really quickly, so it has a very large amount of kinetic energy, the amount of energy it may gain or lose in a collision is going to be small compared to its total kinetic energy. And so in that case, if it's going really fast, we could treat the particle as if it's having elastic collisions, because as a percentage of the energy, it's very close to 0% that it's going to have for its change in kinetic energy. Remember, elastic collisions, you have no change in kinetic energy from before to after the collision. So we can approximate this condition for high temperatures. Now, what defines a high temperature, you might ask? A high temperature, we say in physics, it needs to be far from the liquefaction temperature. What's the temperature of liquefaction? That's the temperature of condensation. So for water boils or condenses at 100 degrees Celsius. So if it's far from 100 degrees Celsius, so let's say 200 degrees Celsius, we would say, oh yeah, that's far away from it. It's probably going to be pretty close to ideal on that first one. If it's only like 5 degrees above, so 105 degrees Celsius, that's not going to be good. What's going to happen is the molecules will come together and they'll have a lot of stickiness compared to their total energy. So they may lose a lot of energy in a collision, or they may just stick together. So that's why it has to be far from liquefaction. So if we're talking about water, maybe a couple hundred degrees Celsius. If we're talking about oxygen's liquefaction temperature is less than 100 degrees Celsius, right? So room temperature is really hot compared to that. So water, we could say it's, got that, not water, oxygen, it's behaving ideally at room temperature. But then we have the second rule. Atoms and molecules have zero volume. We all know that's not true. So what do we say to make it approximately true? We say, well, if the density is low, if it's low density, then the space between molecules is really large compared to the size of a molecule. And so low density is the condition for the second one that we say that will approximate. So if I have something that's high temperature and low density, then I can say this is going to behave like an ideal gas. If it's not high temperature and low density, then you have to use, like I said, the Van der Waals equation to treat it more realistically. So that's what an ideal gas is. So this here is Charles' law, the first one we're talking about, because it's what I ended last class period with. When I put that container into the hot water, the pressure went up. Jacques Cousteau, that's how I learned to pronounce the name from a TV show. Charles, I think is how you actually pronounce the name, something like that. We're in America. Charles. He noted what we saw at the end of last class period. You heat a gas up, actually, this isn't it because this is volume. The volume will increase if you keep it at constant pressure. So that would be if you have like a balloon. A balloon, believe it or not, the pressure inside the balloon is pretty darn close to the pressure outside. The rubber is not making much difference on the pressure. And so if you have a balloon, or even better, if you have just a big empty trash can and you increase the temperature inside, the trash can is going to start to inflate because as you increase temperature, the volume increases. So this was noted by Charles. And one of the other things he noted is it doesn't matter what gas you have, what the initial volume is. If you make a graph of the volume as a function of temperature, you have straight lines that all extrapolate to meeting at one location. And so that was the first hint that there might be some absolute zero temperature. Notice what's happening to the volume at the point where they all meet. It goes to what? Zero. So there is a temperature when it doesn't matter what kind of gas you have, it would extrapolate to zero volume. Now that's not really going to happen because what's going to happen before it shrinks down to zero volume? It's going to become a liquid and then a solid. Right? So that's not what's going to happen, but if you extrapolate from when it's in the gas form back, the extrapolation is that they would all come to zero volume at the same temperature. So that's the first inkling of an absolute zero. So notice this relationship, volume is proportional to temperature. Now, I'm never going to ask you, what is Charles' law? The reason I'm not going to ask you that is we take Charles' law and Boyle's law and Gay-Lussac's law and Avogadro's law, we put them all together to get one equation of state, and that's the one I'm going to refer to. But it's important to understand where that equation of state comes from so we can have some faith in it. So next we have Gay-Lussac's law. I forgot to put that in, not yesterday, I guess it was 2 days ago when I was editing this. Joseph Louis Gay-Lussac came up with this law that is actually what I demonstrate in class, the pressure change if you keep constant volume. And so just like, well, I tried to describe by accident, as long as you have a dilute gas, dilute means a low density, then you're going to have the pressure is proportional to temperature. You heat it up and you keep the volume same, the pressure is going to go up. Looks like we're having some problems with the class with Southwestern. The screen is flashing a lot. Finally, two more laws. Robert Boyle's law, which, wow, I wasn't thinking very clearly. Never will volume be proportional to 1 over volume. That's not a law, okay? Volume is proportional to 1 over pressure if you keep the number of molecules constant and the temperature constant. So that would say if I have a chamber of gas and I keep the temperature constant while I compress it, the volume is going to have to get larger. So pressure times volume is going to stay constant. And finally, Avogadro's law. Amadeo, at least I believe that's his first name, Avogadro was the person who noted that the volume of a gas is proportional to the number of molecules if the pressure and temperature is constant. And so we take those 4 laws and we put them together. So we have volume is proportional to 1 over pressure, and volume is proportional to temperature, and pressure is proportional to temperature, and volume is proportional to N. If we take all of those and put them together, we could, if we wanted to put like volume equals K1.
Thing just switched.
Excellent. Also, it looks like their sound turned off. You guys hear me again, right? But you can't see the screen? You guys see the screen now over there in Southwestern? I can't hear you guys at all, by the way. I don't know what's wrong there. My volume's all the way up. Okay, so we could write this as K1 over pressure, volume equals K2 times temperature, pressure equals K3 times temperature, volume equals K4 times N. And then you could see how we can combine these to get one equation. But that one equation is pressure times volume is equal to a constant multiplied by the number of molecules multiplied by the temperature. Now, something I need to say now before I get too far in, this is what we call the equation of state. It tells us the state of our gas. What kind of gas does this apply to? Only an ideal gas. So this is the equation of state for an ideal gas. And when we say it's the equation of state, what we're doing is we're taking variables that we call the state variables. I can completely describe the system, not the individual molecules, but the system, if I know these 4 state variables. Now, those of you who are chemists will say, well, there also should be one about the chemical potential energy. And that is true. In physics, we never deal with that. In chemistry, you kind of have to. And so in chemistry, you would have another variable to put with this. But our state variables, pressure, volume, the number of molecules, and temperature, if I know those numbers, I know my system. Thermodynamics is an application of statistics. That is, you are doing statistics on all of the molecules around you. And the pressure is a measurement telling us about the average force per unit area caused by those molecules. The volume, of course, is the volume they're taking up, N is the total number of molecules, and T, well, we'll learn more about T in today's lecture. So another name in physics for thermodynamics is statistical physics, because it all comes from applying laws of statistics. And in fact, when we go through the derivation today, students never like derivations, but physicists think they're very important because they show you why we have relationships. When we go through that derivation, you'll see us using some very simple statistical ideas. So there's our equation state, PV equals KNT or NKT. That's probably not the form you're used to seeing, right? What's the form you're used to seeing? PV equals nRT. And so we're going to see that just on the next slide and how the two relate. K, there is a very specific constant. K is called the Boltzmann constant. And that Boltzmann constant, Ludwig Boltzmann is the one who gets the credit for it. It has a very well-known value, 1.38 times 10 to the minus 23 joules per Kelvin. So when you're doing thermodynamics and you see K, it's going to be that specific number. Sometimes we'll put a subscript, take that off, a subscript of B here for the word Boltzmann, because K in physics is an abbreviation for constant. And so we have lots of Ks. Where else have you seen K? Where?
Kelvin.
Okay, the units for Kelvin, that's true. Hooke's law, that's what I was looking for. In Hooke's law, we had the force was proportional to how much you stretch or compress the spring. And so we just had a constant for that proportionality that we called the spring constant, and we gave it the letter K. Right, so when we get to electricity next semester, we'll have a K for the electrostatic force. So K it just means constant. And so you have to be very aware. You know, your equation sheet will start loading up with multiple Ks, and you have to know, in this situation, K is this. In this situation, K is this other thing. Okay, so K is Boltzmann's constant, and it's telling us, you know, a ratio between energy and temperature. The difference in the two ideal gas laws, the one you're used to seeing, the one I showed you, is simply the difference in counting individual molecules or counting moles. So it's Avogadro who gets the credit for defining 1 mole is equal to, was it 1.602? Is there? No.
6.02 times 10.
Yeah, I'm thinking of the charge of an electron here for anyone who cares. It's 6.023, right? Times 10 to the 23rd molecules. That's what a mole is. And you guys weren't here when Dr. Friedline was teaching, but he had all kinds of visual aids, a little mole hat that he would wear. But why would he come up with this? Because it turns out that there are lots and lots of molecules in a room like this. And so it was convenient to use a big number. And actually later on, we'll see that this number comes into play when we do things like calculating the relationship between the atomic mass unit and the gram. But it's the mole is based on how many molecules at standard temperature and pressure have a volume of, 22.4. It can't be 22.4. What is it, 2.24 liters? It is 22.4? Yeah, it's been a long time since I've actually looked at that. I'm going to have to look at it again soon. So we define the number of moles, lowercase n, is equal to the number of molecules divided by this number, which we call Avogadro's number. And so it's a simple calculation. And so if I plug this in, solve this for n, then if I put it into my ideal gas law, PV equals NKT, that equals right, that's just rearrangement for the last line. And so the number R, or the constant R you're used to using, is just Avogadro's number times the Boltzmann constant. So it's simply a combination of two constants to get another constant. So it's perfectly correct to write the ideal gas law either way. PV equals capital N KT or lowercase n RT. It is very important to distinguish then that a lowercase n means the number of moles and a capital N means the number of molecules. So I call it here the macroscopic form when you're using moles. Since PV equals nRT, usually, and especially in physics experiments, the number of molecules doesn't change. In physics, we tend to say, okay, I've got this gas. I could leave it open like a chemist does, or I can just keep it all contained so I don't lose anything. And it's going to be easier for me if I keep it all contained, so we do. And so in physics, almost everything we do has a constant n. It makes physics easier when it comes to this. And R, of course, is a constant. So nR is P1 V1 over T. If you just solve this for nR, divide both sides by T. And so P1 V1 over T1 should equal P2 V2 over T2 if you have a gas that has the same number of molecules and you're just changing the pressure, volume, and temperature. So oftentimes I use this to relate two different states. If I start in this state and I end in this state, I'll just use that relationship because nR should be constant. Should be. It will be in most of our problems. Okay, our first clicker question. Which condition is necessary for the ideal gas law to apply? When I defined an ideal gas, I did not use this word, but later on I did. That would be cheating to answer on her clicker. I know that would not have been intentional.
Oh, he's right. Yeah, that's right.
What? Okay, we have a fairly mixed outcome here. So 18, 11, 2, and 13. Talk to your neighbor. Have them help you out.
Okay, that was just like, okay, it's not B because, and it's not C because he said O2. Right, and it's not B because like, I just picked D, I guess.
Question. Yes, we're going to re-answer.
Yeah, I don't know.
We're going to re-answer, and then we're going to have somebody explain. So go ahead and answer again. This time, your phone shouldn't have told you what the correct answer was, right? All right. Yeah, I got your answer, Paris. Okay, everybody got your answer in? All right. This time, our answers were a little more focused. 35, 8, and 4. So, Rebecca Cunningham, tell us your answer and how you arrived at that answer. Somebody's going to have to turn the sound on there because we're getting no sound. Oh, okay. There was apparently a mute button here that got pressed. Now I have your sound. Okay, so Rebecca, can you answer now?
Rebecca's not here.
Rebecca's not here, okay. All that too. Okay, so then we go to Elara Bankston.
I picked C, but I don't know why.
Okay, pick C, but don't know why. Well, I will tell you why. So, a monatomic gas is a gas with one molecule in an atom. One atom in a molecule. I had the right words, wrong order. Monatomic is one atom is a molecule. So, an example of a monatomic is something like helium gas. It's a noble gas. It doesn't bond with anything else unless you get excited. So that's a monatomic gas. Monatomic gases are actually special in physics. We'll do a lot of work. Oh, great. It says I'm getting an incoming call from somebody. That's, I assume, not Southwestern, so I'm going to hit, well, too late. This system is really on top of things. Okay. It's working for the moment. Okay, so a monatomic gas is important in physics, but in this case, that was not the answer because the ideal gas doesn't have to be monatomic. It does work on monatomic gases. Noble gases tend to be monatomic. Like I said, helium. Noble gases are just the things, we don't have any charge in this classroom, but they're the elements there on the last column of your periodic table. They have completed shells, no partially filled shells. I put in pure because I had noble and I was thinking whatsoever is good, whatsoever is pure, whatsoever is good report. So that was not the correct answer, although a pure gas would mean that you have only one type of molecule. The correct answer was a dilute gas. Remember, we had two conditions for a gas to behave ideally. Those two conditions were that you have non-interacting, which gave us high temperature. And then the second condition was the one that gave us dilute, no volume. And so if the density is really low, which means it's dilute, then it's behaving ideally. So that would be the correct answer there. Gabriel.
What would the density be for a gas where it wouldn't be considered solution?
There is not a clear cutoff, and I can't give you a number. It would depend on the gas, but it's when we look at a picture of a PV diagram, you'll see that it's not a clear point of where it's going to behave in ideal, but you can see from the lines, well, this is clearly non-ideal, this is closer to ideal. Jonathan.
If you want to take into account the fact that a gas is not ideal, does that just change the constant, or do you have to use a completely different equation altogether?
You have to use a completely different equation. You have the van der Waals equation of state, which is pressure minus A times, and I think it's N over V or something like that. I don't remember what the numbers are inside that parenthesis, times, I think it's V plus B times, I think there's something in there. I didn't prepare to talk about this in class, so I don't remember, is equal to NKT. So you have an adjustment for the pressure and adjustment for the volume that are based on the gas.
Okay.
So I know this is a little more nerdy than you need to know, but a few years back, you guys remember the whole Tom Brady Deflategate thing that he finally served the suspension for this year? Well, there were a lot of people saying, well, if you understood physics, you would understand that since PV equals nRT, that given a constant volume in the football, as the temperature drops, the pressure is going to drop. And that's a very true statement. And so I went through and I did the calculation using the ideal gas, assuming that air was an ideal gas. And, it would have to cool down to about 30 degrees Fahrenheit for the minimum pressure drop to have occurred, which to me meant no. So then I was like, well, what if it was cold enough that it wasn't behaving as an ideal gas? So I went back and actually got the A and B and did it with the van der Waals equation. It didn't make any difference. It was still close enough to ideal. You guys may or may not know, here at UNL, there's Dr. Timothy Gay. He has a research group that he calls the Gay Group. They're like the leading group in studying the spin states of electrons. And he was a high school classmate, friend of Bill Belichick. So he went on that good physics says that just should have happened because it got cold. But that's, I think, pushing it a little too much because the temperature just didn't drop enough for that to occur. Okay, so there was your answer. You had used the van der Waals equation. All right, practical things. Just last week, my car, which has sensors to tell me about the air pressure in the tires, said, you've got a tire with low pressure. And so, being the absent-minded person I am, I drove to the gas station, and the the pressures in my tires were all somewhere in the ballpark of 29 to 32 units of pounds per square inch, PSI. Why was the pressure in my tires low? Because the temperature's been dropping, right? It's going to be a beautiful day today, a high temperature of 74 degrees Fahrenheit, but that's nothing like our temperatures we've had in the mid 80s. And so keeping the same volume in there, keeping the same number of molecules in there, the pressure is going to drop. And so I had to go put gas in. So gas, it expands just like most materials do when you heat them up, but it's expanding differently. The molecules, well, that's not where I wanted to go, so I'll stay here. The molecules are bouncing off of each other, and as you increase the temperature, something about them bouncing off of each other is making them so they expand. So, you guys would never do this, but back when I was in graduate school, I had a buddy who was on the football team, and the two of us would go to establishments where they had mosh pits. And, you're out there in the mosh pit, and if everybody's going like this, there's nothing happening, right? And everybody gets really packed in. But then when my roommate and I were good people, okay? We wouldn't go bashing into people. In fact, we took it upon ourselves. There's, people get drunk and do stupid things. And so there'd be people like, hey, watch that girl, and they'd go knock a girl over. I ain't right. My roommate and I were big fellas, so we would take those people out, Anyway, when we started going in the mosh pit, what happens to the density of people in there? No, it doesn't condense. It does the opposite when we start moving fast. The force of our collisions makes everything spread out. People couldn't stay as tightly packed as they were when we start getting a little faster in our speed, a little higher kinetic energy. And it turns out that's what temperature is. Temperature is a measurement telling us how fast the molecules are moving. So this brings us into the last segment of class, would you believe? That tells you 20 minutes of derivation coming up. The kinetic theory of gases. So this is a derivation using standard physics that you know to help us understand what's going on with the molecules and temperature. So this here is not really an important slide. We've already talked about everything. Take a box that has a wall of area A. So A is the area of this entire wall. Okay. And length L. And in that box, we have a bunch of molecules. I'm going to start by looking at just one molecule. And after I made a calculation for that one molecule, then I'm going to take into account all of them. So for one molecule, it hits the wall. If my gas is an ideal gas, what kind of collision is it going to have with the wall? It's going to have an elastic collision, which means it's not going to lose any kinetic energy. That wall is not going to gain or lose kinetic energy. I mean, it's so much more massive, it's basically going to stay put. And so it's going to bounce off with the same speed, but a different direction. But of course, if I'm hitting a wall, notice the x direction here is defined as to the right. If I'm hitting a wall that's perpendicular to that x direction, what component of the velocity is going to change? Only the x component. The y and z are going to stay the same. It's just going to hit the wall coming down, bounce off coming down with the same downward velocity. Only the x direction is going to change and it's going to reverse. So I'm going to have the change in velocity. Well, I'm going to put change in, Since it's in components, I can just say the only one that's actually changing is Vx final minus Vx initial in the x direction. So my change in velocity is all in the x direction. If it came into the wall with the speed of plus Vx, what's going to leave the wall with in the x direction? Minus Vx. And so I should have here then so the change in velocity is minus 2 times the initial speed it had in the x direction in the x direction. Well, I'm going to put that into Newton's second law. I was starting to put a shortcut in case I forgot a step. I was just going to have the steps listed out. That's as far as I got. So the first step in this derivation is to calculate the force that the wall puts on that molecule, or that the molecule puts on the wall, right? Because it's going to be the same thing, just opposite direction. So using Newton's second law, the change in momentum of that molecule is just going to be its mass times the change in velocity. And I'm going to just take this in the x direction, so I drop the vector signs. So I shouldn't have had the minus sign there. So here's where it's minus 2m Vx. So that's the change in momentum. Then I have to divide by the change in time. And this is where things get a little confusing. We don't know how long that molecule is going to be in contact with the wall during the collision. But we can calculate the time from one collision to the next collision with that wall. And so we're going to find the force on the wall averaged over the time that it takes for it to bounce and come back again. So we're going to basically get the average force on the wall due to that one molecule. And so I have to calculate the time it's going to take the molecule to bounce to one side of the container and back. So we're going in the direction parallel to x. What's the length of the container parallel to x? According to my picture, that's L. So if it goes across and back, that means it's traveled a distance of 2L. So I should have 2L is equal to my speed in the x direction multiplied by the time it takes to bounce over and come back. So I can just divide both sides by Vx. And now I have delta t that I will put in right here. So divide it by 2L over Vx. So what I've calculated now is that the average force due to one molecule on that wall is equal to, and you'll notice the 2 and the 2 cancel, and I have then the minus sign, the m over L, and then I have Vx divided by 1 over Vx, which is Vx squared. So that's the force, the average force in the wall due to one molecule. Now this container up here has more than one molecule in it. And so I'm going to have to now generalize and say, okay, I have a bunch of molecules. What do I do to find the average force due to a bunch of molecules? Well, I would have force total is equal to, force 1 plus force 2 plus force 3 plus etc., right? Add them all up. But the molecules don't all have the same speed, right? We know that. They're clearly, because of collisions, they're going to have different speeds. So what I'm going to have to do is say this is equal to the total number of molecules times the average that I get for this force 1 equation if I take all the molecules. Now in physics, we have two ways of indicating average besides putting the subscript AVG. So if you look this up, you will often find that instead of writing force average, they will put force with a bar over it. I choose not to use that notation because that looks too similar to a vector sign to me. And so there's a third way, putting it like that. So we're going to take the average force and so I'll put the entire force equation. I only care about the magnitude this time. What does that minus sign mean in my force? It means it's in the minus x direction. Well, I just care about the magnitude of force. I already know the direction it's going to have to be, going into the container. So I'm just going to drop the minus sign, and I'll have m over L Vx squared. But the mass of the molecules, if they're all the same kind of molecule, I just say, let's choose one kind of gas so they're all the same mass, then I can bring that out because it's a constant. Likewise, that L, the length of my chamber, is a constant. And so my final form here is Nm over L times Vx quantity squared average. Now notice that's the average of Vx squared. It's not V average squared. They're two different things that we'll talk about in a moment. So that's the force. I still have much more to do here. I'm going to add a page here before I forget. Insert. Let's do 2 just to be safe. Okay, so I got my pages inserted. Going to the next page just to continue on. I have molecules that are actually moving in 3 dimensions. So far, I've only been talking about the motion in the x direction because that's the only one that affected the force, right? But I'm going to have, if the molecules are randomly distributed, their average velocity squared in the x direction should be the same as the average velocity squared in the y direction. It should be the same as the average velocity squared in the z direction. So I should have Vx squared. That's an equal sign, you can tell. That should be true just because they're randomly distributed. You can see we're starting to use some ideas of statistics here, finding the average. But also, I should have, it's true that the total velocity squared average is equal to the velocity in the x direction squared average plus the velocity in the y direction squared average plus the velocity in the z direction squared average. Right? That's basically the Pythagorean theorem. And so combining these two equations, using the red one to substitute, notice in the lower line I replaced Vy squared average with Vx squared average, and Vz squared average with Vx squared average, so that that's simply equal to 3 Vx squared average. Why did I do that? Because in real life, we're actually more interested in the speed of the molecule, not its x component of speed. And so now I can replace that Vx squared average is equal to 1/3 of V squared average. So putting that into my force equation, I have a relationship here between force on the wall, the average force on the wall, and the average of the squared speed of the molecules. And I've taken up 11 minutes of my derivation. We haven't gotten to our first important answer yet, but we're only a step away, thankfully. What's the relationship between pressure on the wall and the force on the wall?
Pressure times area.
Okay, we know that pressure is equal to force over area. You said force, pressure times area, same thing. So pressure is force over area. So that means the pressure, one of our state variables, is equal to mass over area times length times 1/3 squared. But for my chamber, the area times the length, it's a cube that I'm working with. What is area times length equal to? Volume. Now, once again, just like when I did the buoyant force calculation, my calculation was specific to this chamber, but it turns out for any chamber I would have had the same result, just possibly much more complicated. It got quite work. Did you have a question, Megan?
Where did the end go?
Where did the end go? Did I forget it?
Yeah.
I forgot it. Yes, thank you. It's important to have it there. Not there. There. Thank you, because that would have made a difference. So that's N over V times 1/3 mass times speed squared, average. Now you look at this, and we're starting to get something that kind of looks similar to the ideal gas law. It's not the same, but it looks similar. So I could take this and say, well, PV is equal to NKT, right? That's the ideal gas law. And taking what we just worked out, multiply both sides by P and PV, or by V, excuse me, and PV equals N times M V average squared over 3, which gives me a relationship between temperature and the average speed. That is, solve this for temperature. I'm going to use a different color to make it stand out. Solve this for temperature simply by dividing both sides by NK. I have temperature is equal to that. So the temperature is a measurement that tells me about the average of the speed squared. The higher the temperature, the higher the average speed squared. So that's our first important outcome there, relating the temperature with the average speed squared. But now let's look at something else. We know that kinetic energy has a simple equation. What's the equation for kinetic energy? 1/2 mv squared. So if I want to find the average kinetic energy, I'm just going to take this and put my little average. But if I have all the same molecules, the mass stays the same. The 2 is a constant. And so that's equal to 1/2 m v squared average. And you'll notice that this here is right there. And so that means that I have the average kinetic energy is equal to 1/2 of, and I'll replace mv average squared with 3kt. We lost them again, apparently.
Again.
Yeah, this is working out well. Okay. You guys back?
Yeah.
Okay. So we have the average kinetic energy is 3/2 kT. This actually turns out to be a really important equation. This here is the kinetic energy related to temperature. It's not the total energy, it's the kinetic energy. If I have a monatomic ideal gas, well, actually, I should be even more clear. This was the translational kinetic energy. If it's a diatomic ideal gas, it could have rotation, so it could have rotational kinetic energy. We didn't take that into account. So really, this derivation was only applicable to, as Ilara said, a monatomic ideal gas. So the average kinetic energy, the translational kinetic energy, is 3/2 kT. In physics, we have a rule that we call the equipartition theorem. And it's, again, actually a statistical rule. And it says that nature will try to distribute the energy equally in all of the different ways it can have energy. If I have a monatomic ideal gas, it can only have kinetic energy. But we call the ways it can store energy degrees of freedom. And it actually has 3 degrees of freedom because momentum can be in the x, y, and z direction. And we take each one of those as a way it can have energy. I know that doesn't make a lot of sense because kinetic energy is a scalar, right? But we say kinetic energy has 3 degrees of freedom, one for the x direction, one for the y, and one for the z. And so the average kinetic energy being equal to 3 times 1/2 kT, those are the degrees of freedom for each molecule, or for each atom if you're doing a monatomic ideal gas. So we have 1/2 kT is the amount of energy in each degree of freedom. And right now it sounds like, okay, so that's really not useful to me. But we will learn later about diatomic molecules, and diatomic molecules have more degrees of freedom. I mentioned this in an earlier class period. It might have been 251. That diatomic molecules can have vibration, and in vibration you have 2 degrees of freedom. One from them behaving like a spring with energy stored in the spring, and one from the actual kinetic energy of their motion. So with the diatomic molecule, you have 2 additional degrees of freedom, 2 additional ways it can store energy because of vibration. But it turns out the temperature has to be reasonably high for it to actually be able to vibrate. And so at low temperatures, you'll still have 3/2 kT. And I have to admit, I may have the temperatures where the next 2 things kick in wrong order. But if you get up to high enough temperature, suddenly you can add 2 more degrees of freedom. And so then it becomes, the total energy is 5/2 kT because you have more degrees of freedom. And you also have rotation. A diatomic molecule can rotate like this or like this. It can rotate 2 directions. There's no energy rotating like this because the masses don't have any distance away, so the moment of inertia is 0. So there's also 2 rotational degrees of freedom. So if you get up to the highest temperatures for a diatomic molecule, you have 7 degrees of freedom, 3 for translation, 2 for rotation, and 2 for vibration. And so it becomes 7/2 kT because you put it in 7 ways. Okay, we're out of time. That's a good place to stop, except for one question. Where's that one question? According to the kinetic theory calculation that we just completed, which kind of energy is proportional to the temperature in an ideal gas? Okay, because it's 30 seconds after class ends, I'm going to just stop it here in 5 seconds. So make sure you have your answers in. Okay, we had 1, 20, 24, 0, and 2. The correct answer was my derivation was only the translational kinetic energy. That's what my derivation was. And then we saw that it was also the total energy, but it was a different relationship depending on the type of gas. Okay, have a great